So, dear colleagues, allow me to introduce you Petr Kolínský, who joined our team on structure of the lithosphere this January, after his coming back from Vienna University, where he stayed for 6 years, from 15 to last year. He finished his studies at the Charles University, Faculty of Mathematics and Physics, specialization Geophysics in 2003, and then at 2010 he received a PhD also at the university. Then he worked with structure mechanics and everyone knows that. And now he is in our team, and he is specialized on surface waves. You will see his lecture. Thank you.
Thank you. Welcome, everybody. So you have already seen part of the animated figures. So, so thank you all for coming, and also hello, everybody on Zoom, if there is anybody. When I was thinking about the lecture, about the talk, I was like, okay, let's say from the very beginning, what could be my aim, or what I would like to show you, or what I would like you to take the message from this lecture. Let's say I would be very happy if at the end of the talk, you will understand what's on that figure, how we measure it and how we model it. And if you do, then it's all perfectly fine. Then my plan is that I will explain you in like 40 minutes what's behind this, what does it mean, how we measure it, how we model it. And I was also thinking about how to like structure, if it's structured at all, the lecture. And I decided, because I will talk about something which is kind of new, not that well established in seismology. So I decided to go over the, let's say, my like experience, how I develop these things. So it's not necessarily like structured by like topics, you know, starting with some methodology and so on, but more like about how I really develop the story. So let's see if we don't get lost in all this. So, but I don't see. So yeah, because at the first slide you only saw my name, so let's also list some other names here. So as Jak already said, I joined the group of the Litos team, as we call it here. So you see some name of our colleagues here, which I'm working now intensively now. Most of the work which will be showing you today has been done in the last 6 years at the University of Vienna. So I'm listing some names of people working there and helping me develop these things. And some of the methods used actually go back to my previous employment at the Institute of Rock Structure and Mechanics. So this is why I'm listing also some names here. So what will be kind of the topics, or like broader topics of the talk today? So we'll talk about the measurement of surface waves, of some observables, mainly arrival angles, group velocities, phase velocities. I will then show you something about the modeling. I was asked not to make the talk too technical and too specific, so, but still it's seismology, so let's see. I will try to keep it to minimum. I will show you how all these things can be used actually to invert and to detect some remote, distant anomalies in the upper mantle. Then I have a chapter about the dispersion curve. Let's see if I will manage. If it will be too long, I will just simply skip it because it's a little bit too technical. And also, if you will follow closely the talk, I have kind of, I call it USRE quiz. It's more like a joke. And I already used that joke once. So if you know it, if you have seen some of my previous slides, okay, repeated joke is not joke anymore, but okay. So what I will be showing you is based on these 3 papers. So most of what you will see is already published, but at the end I will show some like ongoing work under construction. So this will be something new. So let's hop on the topic. So what will be the sources of long period surface waves? These are obviously big earthquakes in our case. So here on the map you see 20 or 30 earthquakes distributed all around the world, kind of covering as possible all the azimuths. What will be the receivers? Most of what I will be showing you is basically all is based on the AlpArray data. AlpArray was a project covering basically this alpine region. And in addition to the AlpArray stations, I've also used some stations around, basically covering the whole Europe, roughly 900 stations. What is the data? These are the broadband records of seismic waves. And so you see here something like 2 hours after a big earthquake. And if you just filter it, looking at longer period parts, you see nicely the surface waves here. Because if I show it here, they don't see it on Zoom. So it's the surface waves. So let's now go for the first topic, group velocities. So very simple thing, I would say the simple thing which seismologists can do is that you have your record, you pick one value of arrival time on your record and you plot it on the map. And you do it for all the stations, station by station. So it's like very simple thing. So what we do here is we have different periods of waves, and we calculate the envelope of these waves. So we can pick the maximum of the envelope, which corresponds to propagation of the energy, which is here or here. Or we can also pick, let's call it phase or zero crossings in this case, very simple, simply really the carrying wave, the wave itself, which corresponds to the ground motion, velocity in this case. And let's pick these times and let's plot it on the map to see what happens. So very simple example, there is an earthquake from Kamchatka. By these magenta lines, you see the wavefronts, really the phases. You don't see anything special, I would say. The white lines are the great circles, or let's say the circular wavefronts. So, okay. If now I add the group propagation times, group travel times, you see they are like a little bit undulated, but okay, I would say still nothing special. Let's go for another earthquake. The same, somehow circular wavefronts, adding group travel times. You see they are a little bit more undulated, but okay. And now let's go for my favorite earthquake from South Atlantic. I will talk a lot about this one, so you can remember it, magnitude 7.4. Again, so it's propagating from more or less from south or southwest. You see the wavefronts. And when you plot then the group travel times, it looks like way different or somehow, somehow weird. And first I thought that something is wrong here, but then I did some test analysis and everything looked good. So the question was, what could it be? Because when you look at this, let's say, difference between the most delayed and most advanced energy, it's 110 seconds and it's 100 second wave. So it's more than a period. So, okay, the question is, how could this happen? What does it mean? So here now, let's go for the animated figure. So basically here you see that 100-second wave propagating through Europe. And what you see by the contours and by color, it's really the energy. So basically the envelope of the waves. And you see that the pattern a little bit changes, but more or less from the top to the bottom, from the bottom to the top, it keeps the rough pattern of these delayed and advanced parts. Okay, once more. So the question is, if it's like real or what does it mean? How could this happen? Now I need to switch back. So I was advised by my colleague in Vienna, Götz Bockelmann, to look at the paper from 2000. You actually cannot see it. It's by Koos Nold and Tony Dahlen from 2000, so 22 years old paper. And Götz told me, don't your like wobbles on the travel time, maybe don't they look like these models which these guys have in the paper? And so this is how we got the idea. So what's the point of this modeling, or what does this mean? This paper says that if you have a scatter or anomaly, let's for simplicity talk about low velocity anomaly, and if it's hit by, in this case, plane wave, it's clear what happens. Then there is like a low velocity anomaly, the wave is like bended, it's like delayed. And what happens then if the wave field propagates, that after the anomaly, that delayed portion tries to get faster and faster. So it's so-called wavefront healing. So this we all know, that's like a very simple thing. And even the paper says it's about healing. The most important thing is that not only that the middle portion is healed, but the disturbance propagates laterally, which means that the middle portion is healed, but not only it's like getting faster, but those like lateral wave parts, which are faster, are delayed. And this disturbance propagates as you go farther, creating like repeated wobbles on the wavefront. So it's not like just one wobble, which it was at the beginning, but it like propagates to the sides, which is something like very interesting. And actually that paper is not even like cited that much. So what I did was that I just took this equation. I don't go into the details, but basically the paper shows that one equation. And if you just code it, which is like kind of easy thing, you may model the wave field. So here by the same two colors, you see the wavefront, by the magenta, and by the cyan, you see the group travel times. And then I was thinking, okay, maybe really these parts kind of resemble really what I have measured. So let's now change the projection to somehow see it like in Cartesian coordinate system. So this is still the F, but somehow the map projection is changed so that really now the circular wavefronts are like plane waves here. And I was thinking, could it really be that what we observe is due to the scattering and due to this, let's say, healing and creating this pattern? And if you look at this pattern, the question is, if you model low velocity anomaly or high velocity anomaly, which of them could it be? And looking at these patterns just visually, now it's like purely like qualitative analysis. I was thinking, okay, maybe what I measure really fits to that yellow square up there. And if you zoom in, it really looks somehow similar. You don't find anything like this on the right side of the figure. So then I said, okay, if it's a scatter, then it needs to be a low velocity anomaly. So based on the shapes of the group travel time. Then later for the paper, I prepared such a figure which basically confirmed this. So on the left, you see the measurement. In the middle, you see the synthetic low velocity anomalies and the pattern caused by low velocity anomaly, and right, the high velocity anomaly. And you see that it's like flipped, how to say it, like that these delayed parts are like more broader and the fast and are more like, let's say, narrower. So just like visually, it fits more to low velocity anomaly. And now, okay, if it's an anomaly, how can we guess where it was or how far it happened? Or so what I did was that I took a second earthquake in a similar region, also South Atlantic. I did the same analysis. So let's call it green and red earthquake. So you see the group travel times from green and red earthquake. And you see that the shapes are very similar to each other, but they are like shifted. In this case, left, right, or let's say east, west. So the question was, if it's really a scatter, and if really the shapes are the same, so let's have a hypothesis. It needs to be the same scatter for both earthquakes. Here you see how the earthquakes propagate over the globe. So they are actually very close to each other. What I did was that I simply measured what's the distance of the earthquakes, which is roughly 400 kilometers east-west. And what's the distance of the stripes, which we measured? It's roughly 200 kilometers east-west. And I said, okay, if it's really a scatter, which creates a pattern, that scatter needs to be roughly 2 times closer to the measurement than to the source. Why? Because it works really as if you have an obstacle and you take your light beam and you move it, so the shade on the wall moves to the other side, and the similarity of triangles gives you the distance, right? So if it's 2 times more distant here than at the measurement side, the scatter needs to be 2 times closer to the Europe than to South Atlantic. So my guess was that it's somewhere here. And why we know that it's east of the rate path? Because the modeling creates that V-shaped pattern. So it really points you to one direction of the rate path. So now it points really to the east. So here you have an animation, how the different properties of the anomaly changes the pattern. So basically you see if you change the frequency, the pattern like closes and opens. If you change the strength of the anomaly, it really creates like higher and lower wobbles. The width of the anomaly also changes the pattern and the background velocity as well. And basically the most, I would say, prominent evidence that this hypothesis was right was when I did the measurement for different periods. So you see the period changing here. For those looking at Zoom, it's the small number here. So on the left is the measurement, on the right is the modeling, and you see that it really behaves the same. So basically, for different periods, the pattern shifts to the sides. So just manually, again, still qualitative analysis, I said, okay, the scatter needs to be somewhere here. So I a little bit played with it, and then I managed to fit both the red and green earthquakes with the same anomaly, with the same properties, with 2 patterns. Okay, let's go back to this, how big the anomaly needs to be so that it really creates the pattern. So I showed this on several conferences, and the comments were very skeptical and very, how to say, like, yeah. I especially like this one saying that, I don't rather say who was it, but that it's conceptually interesting, but, and then, so I was thinking, okay, do we have something more to really see if it's really true? So let's look at phase velocities now. We have a different method, again, not to be too technical, array approach. So basically now we take several stations in that circle, which you see here, and we measure the differences between the stations. So basically, if we have the geometry, we have the time delays between the stations as the wave arrives. It's like very simple linear equation so that you can really estimate the vector of the slowness, meaning both the magnitude of the velocity and the direction. So very simple thing. And the way how we plot it is that by color, I plot the period. By the position of the vector, I plot really the direction of the velocity. And by the length of the vectors here, I plot the velocity itself. And the idea why I was doing this was that, okay, let's map the velocities over the alpine region. And let's basically do something like a tomography without tomography, really just like map the velocity. And I was so disappointed that it didn't work. So I did it here for many periods. Maybe if you look at the very left uppermost one, maybe you can guess that these are some mountain routes there, maybe. But other than that, it didn't show anything. So these are just like patches of green, yellowish, having nothing to do with the structure. So I said, okay, let's forget it. And let's think what's wrong with the method. So I was thinking, is there anything like more systematic or something which we can really focus on if these are not the velocities? And then I got the idea, let's plot not the velocities, but let's plot the other component of the vector, which are the angles, meaning the directions. So I did, and suddenly for all earthquakes, I started to get some systematic, let's say, stripes. So this is the big Mexico event from 2016 or 17, magnitude 8.2. And this doesn't look like random, you see some stripes. Then I look at other earthquake, my favorite South Atlantic, for 8 periods, and you see clear stripes of positive, negative. So again, what you see here by color are the deviations from the great circles, meaning that really it's in degrees, plus minus 20 degrees, how much the wavefront deviates from the great circle. And you see clearly positive, negative stripes. And then I did it for all the earthquakes. You will see 21 of them here. And if you a little bit like close your eyes and look at all these are small, you see the stripes everywhere. So it's not like coincidence. Don't worry, I will show you bigger here. So these are 6 earthquakes, 1 period, only 50 seconds. And these are in pairs. So at the top, you see the two earthquakes coming more or less from the north, in the middle, more or less from east, and here, okay, southwest and from south. And you see that the stripes are everywhere. And they clearly depend on the direction of propagation. They have nothing to do with the local structure because they wouldn't be that dissimilar earthquake by earthquake. Then I was looking at literature. So now I will show some papers from US array measurement. And if you look at these papers, the stripes are everywhere. So you may look at these are amplitudes or also azimuth variation. They call it like belts or band-like patterns or what's here, striping pattern or banded appearance or belt-like pattern, whatever. This is, by the way, from China. These are, the others are from US array. So these stripes were everywhere. But in none of the papers, they explain why the stripes are there. What does it mean? And in most of the papers, they speculated that it's something of the local structure, because at each of the paper, they only look at 1 or 2 earthquakes. But if you look at many earthquakes from all the directions, it's clear that it cannot have anything to do with the structure under the area. So I got back to the modeling. So at the top, you see these delay times, the original equation from that older paper. And I said, okay, if I have the shape of the wavefront, which is the delay times, it's super easy to calculate the angle because it's just the perpendicular direction to that wavefront. So basically you make a derivative of the wavefront and you have the angle. So suddenly, very easily, adding 1 line to the code, I have the modeling of the angles. And I started to play with this. So here you see it's like a real scale of the global map. If you see really the map, so it's like the map of the world. So 3 hypothetical earthquakes, 3 hypothetical heterogeneities of different width and of 7% strength. And I just model how these arrival angle deviations would look like if I really have something like this. And so what's striking here is how far these disturbances propagate. Basically, here I just plotted it to 10,000 kilometers, like 90 degrees distance, but you still see that it's not 0. So again, the scale is minus to plus 20 degrees. So here I will just flip between these 2 slides. They only differ by the period. So this is 100 seconds, this is 50 seconds. So you see how it changes. So if we have the measurement, if we have the hypothesis, and if we have the modeling, let's do the proper inversion, right? To see where the scatter is. So let's take now 3 earthquakes from the South Atlantic, my favorite location. You see that at 100 seconds, we see 3 similar patterns just shifted. We now know why they are shifted, because the earthquakes are shifted. So it's like that similarity of triangles thing. And let's look at it. We have a rough idea that it's 4,000 kilometers away. We know it's a low velocity anomaly. This we know from the shape of the groove travel times. And we know that it's east of the ray path. So let's make a grid here. And let's simply just check all these points to see where the anomaly is. So more specifically here, 3 earthquakes, this is the grid. And actually I was looking not for only 2 parameters, but for 5. The position, the width of the anomaly, the initial time delay, which is basically the strength of the anomaly, and the velocity, the background velocity, which is basically the global Earth model. So the point which was fitting the best is that one which you see by green here. So you see longitude, latitude. Here you see the circle, the great circles connecting the earthquake and that point, and the results for the width of the anomaly, 350 kilometers, initial time delay, almost 60 seconds, and the velocity, which by the way is exactly for the period, which is 100 seconds. It's exactly the velocity of the PREM model, the preliminary reference Earth model. So basically just by the inversion, the velocity which fit the best is the 1D Earth model. So it was not surprising, more or less confirmation that it could be so. And if you now look at the models, you see how that anomaly, that pattern fit the 3 measurements. So just again, how the angles propagate, or the wave disturbance propagate. Okay, and then the guess was, what could be the highest, let's say, strength of the anomaly, because you only had the time delay, so you don't know how the anomaly, how big the anomaly is, how long it is, because there is a trade-off between the strength and the size, obviously. So if I said like maximum could be 11%, then the anomaly needed to be like almost like 2,000 kilometers long. So yeah, that's the anomaly. So now I will play for you several slides to show you how the dependence on period looks. So it's basically a zoom version of the previous slide. So it's 50 seconds, 60. So what you see in the magenta region is the measurement, and what you see in the background is the modeling, right? So I'll go back. And 2 things which you can notice here. For example, if you look at 50 or maybe better 60 seconds, you clearly see, especially on this left earthquake, let's call it left earthquake, that there are stripes pointing in a completely different direction. So at the end of the talk, you may think or may discuss what you think is the anomaly here. If you look for it longer, especially let's say 100 or maybe 90 seconds, I would say I can fit the stripes pretty well. But on that right earthquake, you already see that there is a positive stripe here, which I'm not able to fit. And here you see it in there. So again, the question is, what could it be? And I have some explanation. But other than that, okay, the main bulk of the pattern could be explained. Again, a little bit technical slide, just because there were so many skeptical comments saying the method is wrong and the calculation is wrong and it's like old paper, nobody cites that paper of Nolan and Down, so how can you use it? I asked my colleague Felix Schneider, because I knew that he had a method which is completely different. It's based on this Korniev and Johnson paper. It's like analytical method of calculating the wavefield. So I asked him to basically calculate for me the same thing with his method. He did, and we got the same result. So kind of, okay, this is just comparison of the 2 methods. So I will not go into the details. But this was a confirmation that the method by Nolan and Down is not completely wrong. And it's very efficient because the Korniev and Johnson method is like iterative method. So as you go for higher frequency, it takes like insane long to calculate, because for like every position from the scattering, you need to calculate the wavefield and propagate it. So it's like very inefficient. That method by Nolan and Down is very fast because you only get the location and you evaluate the equation and you get your travel times. For those who are familiar with sensitivity kernels of surface waves, if you up to now thought that I'm just showing you something completely like new and something which has no relation, no, it's basically the same as sensitivity kernels. It's perfectly equivalent. So what are the sensitivity kernels? Or let's say, what do you see here are the Fresnel zones. So if you have your earthquake, your station, you can plot a Fresnel zone. So each Fresnel zone is basically, if you have 2 rays, one is direct ray, the other is like the ray which has a scatter somewhere here. Basically, every Fresnel zone tells you what is the difference, and if the difference between the 2 rays, like skips one cycle so that it's like constructively or destructively interfering, you move to the other Fresnel zone. So basically, these stripes of the different Fresnel zones exactly correspond to the stripes when I do that modeling, propagating the arrival angles from the so okay, now the question is, okay, what is that anomaly? So we got the location here. I did it for several periods. And now the question was, do we really see somewhere here in Central Africa? The answer is obviously yes. It's something what's called Cameroon volcanic line. I will not go into the details what it actually is. Is it a plume? Is it a hotspot? Okay, it is a hotspot, but what's happening down there? Actually, there is this like chain of volcanoes which may resemble well-known chain of volcanoes like hotspot tracks like Hawaii or Yellowstone. But these volcanoes do not show the age progression, meaning at some period of time, all of them were active simultaneously, which somehow corresponds to that. Let's say here it's like on scale, if you take this rectangle and you just shift it by the dashed lines to that region, that the anomaly really needs to be very long. So it's not a localized plume-like anomaly. It's really like very narrow and very long anomaly. But yes. Is there something in the literature which could be related to these things? So, because I have discussed it a lot with Barbara Romanovic, I also look at her papers. Actually, she's doing something similar with body waves, looking at the roots of the very deep plumes under Hawaii and under Iceland. It's something completely different in terms of waves methods, but the idea is the same, meaning you have something small and distant, let's say smaller than the wavelength, and you use it as a lens. Basically, you have a wave field which is disturbed by this anomaly. And what you measure is not like a global travel time or like global time difference across the anomaly. What you measure is the shape of the wave field under your array of stations. And from the shape of the waves, you guess what was the scatter causing this disturbance. Dispersion curve, okay. Let's go quickly. This was the optional chapter. By the way, I very much like looking at very old papers, so I just used some figures here from very old papers. If you look at any dispersion curves of surface waves phase, I'm talking about phase velocity curves, what's striking is that they are always monotonic, meaning here it's period and the velocity only grows. It was the same 100 years ago, the same today. If you get measured dispersion curves, they have some undulations. So here, I'm showing one of my very oldest papers, different method. You see very wobbled dispersion curves. I'm also showing now some other papers. You see that it's not like just my method which produced the bubbles, but every dispersion curves show these, let's say, undulations or fluctuations. And if you look at the model, models are always monotonic and smooth. And the question was, or the idea was, could these wobbles on the dispersion curves also be explained by the distortion which I've been showing before? So another paper also showing array measurements of dispersion curves, meaning if you have like small array and you do this like plane wave fitting, you also get these wobble dispersion curves. So basically, what's the main problem here? It means that when you measure this wobbled curve, it cannot correspond to the structure because no structure gives you such a curve. Basically, you cannot create structure. And it doesn't matter if it's 1D, 2D, 3D. In any structure, you always get monotonic curve, but by measurement, you always get wobbled curve. So there is a discrepancy. So what I did was, I again use AlpArray, I again use my favorite South Atlantic earthquake, and I simulated these two station measurements and some other array measurements. So basically, I took the difference between the two stations. So at many profiles, you see it here by the orange lines. I measured the wobbled curve, and then I modeled the curve. How could I model the curve? It's very easy, because for any point on the Earth, with my modeling, I can estimate what's the time delay, which is positive or negative, meaning the wave is delayed or advanced. So I can very easily simulate the curve, because basically I just make the difference of the two points. And I got the wobble dispersion curves by the model. So by color here on the right, you see the curves modeled, and by gray, you see the curves measured. And even the measurement does not fit perfectly to the synthetics or the other way around. The main features are preserved. So if you look at this, so this is the westernmost profile, meaning this one, and this is easternmost, meaning this one. And if you look at the wobble, meaning, let's say, this low velocity anomaly here, if you go from west to east, it like shifts with period. And it's clear why, because we know that the pattern opens, that V-shaped pattern opens and closes when you change the period. So I did it for many profiles, for different lengths of profiles. I did the modeling. I always got confirmation that the, let's say, the fast and low wobbles of the curves fit. So here's the explanation how, let's say, in the middle by the cyan line, you have the structural dispersion curve. So again, all the modeling is done in 1D. It's just prem, it's 1D. There is no structure. It's 1D. And by these stripes here, you see that, let's say, the positive and negative delay times. And it's clear what happens if you have two stations and one is in the delayed stripe and the other one is in the fastened stripe. Then the time difference is apparently what, larger or smaller. If it's fast, it comes early here, it's late here, so it's apparently long, meaning the velocity is apparently low, and the other way around. So these wobbles which you see on the dispersion curve can be explained by these delayed and advanced part, which is like purely interference phenomenon. It has nothing to do with the structure. And this is also why these curves don't correspond to the structure. So the bad news here is that basically, and you see how big the difference can be, because here you have the structure. I got lost my eyes now. So this cyan line, it's the, no, you don't still see it. So this is the structure, the smooth monotonic dispersion curve, and this is what you measure in that structure. So now the question is, how that wobbled curve can be related to the structure. And I remember when I showed this, I think I can tell his name, to Lapo Bosky. He was looking at me, being so shocked, saying that he now thinks that from now on, we should not try to do any tomography anymore. Because basically what you do is that you like enter to tomography these wobbled curves. And this is the structure which like, has nothing to do with these two. So another message, people often think that if they use array measurements, meaning that they measure not only the velocity, but they measure also the angles, that it helps to get to the structural velocity. And it's not true, because if you do the same synthetic measurement of the same synthetics with the array measurement, knowing the angle doesn't help you. You get again the wobbled curve the same as before. So what I did 500 array measurements here. So every circle is the array measurement. Again, 1D structure, purely synthetics in 1D structure. And I got these 500 curves here, which you see here. So again, this is the structure, and this is what you measure. So the question now is there something so that we can like remove the wobbles, knowing all this modeling, all these hypotheses? I gave the label under construction here because I have no answer in the moment. I'm just trying. I have a clear way to go, but it needs some heavy calculation, which I have not finished yet. So I made some like qualitative guesses, and I'm not showing the equation here because it's not properly right. But what I have in the moment is that basically here you have the synthetic measurement. So you see how wide let's say the scatter is. And after applying that correction, which is not really well developed yet, I can make it 10 times better, meaning getting closer to the structure which I want to get. Structure again is that sign. So let's look at the, let's say, ongoing work. So I apologize for those who know this US array quiz. So let's look at this paper by Liu and Hall from 2015. It's a paper, 20 pages, full of stripes. I think, again, if you a little bit close your eyes, you see clear stripes in this measurement. And actually, it doesn't matter what quantity it is. This is something what they call divergence B, where B is a gradient of the time delay. So it's like a second derivative of the time delay. It doesn't matter. If you have a quantity, you can make a derivative. It always shows the same stripes. And when I was looking at these, and they again speculated, how could it be that the structure produces these like weird stripes? But I don't believe that in Eastern US they have so regular, like slow, fast, slow, fast, slow, fast structure. So now the question is, what could be the anomaly causing this? So I'm giving a hint, plotting the whole US now on the left. And I think I was first time showing this in AlpArray meeting in Frankfurt. And yes, you are right, it's the Yellowstone plume. So I did the modeling for the Yellowstone, taking some positions and some like properties of the Yellowstone plume from some papers. And if you model this, you kind of, I would say, qualitatively get the same stripes. So actually, it's now idea which we are developing with Cedric, who is sitting here, to get a little bit closer. So we plan to look really to the data of US array as well, because the Yellowstone plume, it's one of like rare examples where you have the dense seismic network really around the plume, which you don't have in the oceans. Another example of ongoing work, because I see clear stripes from the earthquakes coming from north. So here I try to invert four earthquakes coming from the north. It looks like it's pointing to that Jan Mayen plume in North Atlantic. I'm able to fit some stripes here and here, not really that much here and completely off here. So probably the earthquake is hitting some other plume. I'm also trying to get the point of what could be the anomaly causing the stripes coming from the earthquakes from Mexico and Guatemala. Here you see that it does not fit because the angle of the stripes, here again is a measurement, is a little bit different, but like, okay, I'm trying, so it's under construction. By the way, what you see here is something, it's like very enigmatic thing, like Bermuda hotspot. There is something in many tomographic maps, and also in that paper, they have that small plume under the Bermuda hotspot. Also, one reviewer asked me, okay, you see it on the Z component, do you see it on the other components? So the answer is yes. Even on the radial component, it's obviously way worse because of the noise. So one of the plans is also to look at love waves, meaning transverse component. And this is a slide showing that basically having all these ideas modeling, we can really model any dispersion curve with any wobble. So here you see the dispersion curves and here you see the angles. That slide also gives the answer. At the very beginnings, I started with saying that when you plot a map of velocities, you don't see anything systematic. But when you plot a map of these angles, you see the stripes. So the question is, these are just two components of the same vector, basically the length and the position. How could it be that the length of the vector doesn't show anything systematic, but the position of the vector does? And here in the modeling, it's all explained. So basically, what happens if you model the dispersion curves adding the structure beneath the array, the velocity is obviously very much, meaning the magnitude of velocity, is influenced by the structure under the array. So you have your pattern coming from Central Africa to the Alps, and the velocity beneath the Alps shifts or like influences a lot the velocity. So this is why you see these patches, because basically it's like modulated time delays from the scatter and the local structure. But the angles, which you see here, are not influenced that much. So basically what you see here is 20 curves for 20 different cases of the local structure beneath the array. And you see that obviously they shift up and down when you change the velocity, but the angles almost don't change. So that's kind of the point, that you need to look at the angles to see the stripes. This is just to show that basically having this modeling, we are able to model whatever quantity you want to. So group velocities, phase velocities, angles, also amplitudes, time delays, derivative of all these in space. So, and these can be used for some other cases. This is kind of a feasibility study, which we did also advised by, I was advised by Cedric saying, maybe in Europe we also have a plume which was or is close to the dense network. So this is the Eiffel plume. So I did some modeling to see, you see that because it's a small plume and because we are close to the network, the stripes are very thin. So probably I'm not able to see these with my array measurements because the arrays are way bigger than the stripes. So probably we need to develop a little bit different technique of measurement. And one thing which we also would like to try is, can we see the same thing from ambient noise cross correlations? Because up to now I was showing only the ethnic. So that's the plan. We submitted a project proposal, so I also thank those helping me, which was Christian sitting somewhere here, and Honza Bojanek also helped me a lot to develop the proposal, not even mentioning Jarka, obviously, and the others. So messages. I'm not sure if I need to repeat it. Basically, yes, we can explain the patterns by wave interference. It brings us the information about remote structure anomalies. We can estimate the properties of the anomalies. And the whole modeling can like explain the wobbles of the dispersion curves, which have some implications for the local structure measurement. Yes. So some acknowledgements that you think that this is my last slide, but that's not true. This is my last slide, but I will not talk about this. So if we now move for the beer, we can discuss the AlpArray, which is like a project prepared for next 2-3 years. So thank you.
Thank you very much, Petr, for a brilliant talk. And I believe there will be a number of questions from the psychological community, others perhaps as well. Christian?
Just thinking maybe another step ahead. Referring to that comment by Velocities, would it be a nice follow-up exercise to take a surface wave topography study, apply the de-wobbling of the dispersion curve and redo it to see how much of the structures that image actually change?
Yes, that's a good question because that's exactly my plan. Actually, I'm now working on the tomography. Yeah, on the first step, it's more or less really the tomography, including the wobbles, and I especially included the earthquakes with huge wobbles. Actually, the first task is to show, because what people do many times, that they simply cut off the wobbles for the tomography. So the first question is, if we input complete wobble dispersion curves, which at some point reach really plus minus 10% into a tomography, and if you have really high density of rays, does it actually matter? Because in the end, my preliminary results show that if you have really, I'm talking about like tens of thousands ray paths crossing the Alps, if you enter something like this, in the end, you get the structure anyway. And this is why tomography works in the end. So the question is, where is the threshold? Because in the end, if you can really remove the wobbles, it would allow you to actually lower the number of measurements, right? But yeah, that's absolutely the plan, yes.
Other questions?
Nice results, thank you. You showed effects of different frequencies. Would you recommend to concentrate on certain frequencies, longer or shorter, or just the idea is to implement as many possible frequencies?
Yes, the idea is that for each earthquake, I look at the broadest range I can really like reliably measure. And I would maybe go back to the slides where I told you that at the end, you may guess what is the, simply, I would say at different frequencies, having the same earthquake at different frequencies, you see the stripes sometimes pointing to different directions. And it's somehow clear, it's here. No, you still don't see. How do I? And the point is that it's the same like with any measurement of surface waves, that the frequency gives you the depth extent of the anomaly. So obviously there are anomalies which have like only, let's say, shallower depths, and these are pronounced in shorter frequencies. So, I'm not sure if I can go there that quickly. And the point is that during the talk, I asked you a question, what do you think could be the... Yes, here you see it for... it's not well visible. But basically here at each panel, you see the different frequencies, and you see that the pattern not only shifts left, right, or like laterally, let's say, from with the frequency, but sometimes it completely changes the direction. Where is it?
This is clear, but my question is whether to prefer certain frequencies or better to use as broad spectrum.
Yes, I wanted to show this slide. I think that it depends. For example, here at 60 seconds, I would still say I can see some stripes of that Cameroon volcanic line. But what's more pronounced here are these stripes pointing more to the west. And it's certainly something different. My guess is that's this Cape Verde or Azores Islands or Canary Islands thing, because it's pointing exactly to this. So in this case, I would try both. I would do the same research on the other plumes over there. But these are only visible, let's say, at 60 seconds, maybe a little bit here. But when you go to 80 seconds, they are completely lost. It could be because of two things. First, the depth extent is really that shallow that they don't show up here. And second, that pattern from the Cameroon volcanic line is so strong here that like overbeats the others. I'm not sure because my modeling in the moment is only capable to model one anomaly at the moment. So the other step is to do the full waveform not inversion, but full waveform modeling so that I can enter two or more anomalies to see how the pattern like overlays one to the other. But I'm always trying to look at the broadest range I can get from the earthquake. And then I say, okay, in this range, maybe I see Canary Islands. And that range, I see Cameroon volcanic line.
Thanks.
Correct me if I'm wrong, but there are published finite frequency, so-called finite frequency tomographies based on the surface waves, and they are giving 3D velocity structures around the world, upper mantle, let's say, and really somehow implicitly take into account all these very nice effects that you somehow pinpoint or identify? Are they like inherently included in those travel time, finite frequency travel time tomographies?
In some, yes. The point is that if you look at these tomographies, what they usually do is that they use these sensitivity kernels, as I was showing them at some point. And they cut off these kernels at some given Fresnel zone. So usually they take 2. If they are really brave, they can take 3 or 4 Fresnel zones. What I was showing at some slide, I will not look at for again, that Cameroon volcanic line lies in a 6th and 7th Fresnel zone producing this pattern. So for example, if you go for this and you use only 3, 4 Fresnel zones, you wouldn't see it. If you go up to 10 Fresnel zones, you would, or you should, I would say, yes, exactly, because it's exactly the and at some point, I was also showing, I didn't talk about it, but when I was showing the results for the, these are the so you can clearly see this is the 6th Fresnel zone. So if your sensitivity kernel only takes into account this, you completely miss it. But obviously, because you may have a global tomography, to some extent you see it, and this is what's shown here. The background is a tomography result from Eric de Bail's paper. And you see that indeed there is some low velocity zone here, but it's somehow smeared here and over there. So basically, if you take my low velocity zone and you shift it here, it would kind of fit. Why? I mean, what's the difference is that there is like inevitable smearing in the tomography. So his low velocity zone is, let's say, only, 4, maybe 5%, -5. That color could be somewhere here, maybe -6. And to get a reasonable length of, let's say, my anomaly, I need to go for 10 or 11%. So what I'm saying is that I can have a smaller and narrower anomaly, which is probably stronger to get these strands. While in tomography, it's all like smeared. I'm not saying this is better in tomography. I'm just saying it's like complementary. You can get some more information. But it's actually really important for the full waveform calculation, because when you do this full waveform, I'm an expert on this, you also need to take into account some region along the ray path. And again, it depends. If you take 1, 2, 3 Fresnel zones, you don't get anything. You need to really go for high Fresnel zones to see these effects.
Are there any other questions?
Small technical question. At the beginning of your presentation, you showed some waves from different directions, rather from Kamchatka. Can you show me this at the beginning?
How to navigate quickly is because
I don't understand the curvature of this white line, so I will need some explanation.
Yeah. So now we got. I go back to the presentation notes. Já to pak nezobracím. Když ukážu tenhle, tak oni ho nevidí. Takhle. Function shift. Yeah. So yes.
This is Kamchatka.
This is Kamchatka.
And white lines are what?
White lines are the geometrical wavefronts, like circles, simply circles plotted with the center.
It's 20 degrees from north for Kamchatka.
Probably yes, something looks like.
So it would. So I would guess it would be curved on opposite side.
It's just a matter of the projection, because it's not it's like some kind of cylindrical projection. So it's just a projection that is bended, but you are right. In this distance from Kamchatka, obviously these are circles which are bended towards, because the center is in Kamchatka. Yeah. It's just a projection of the map. If I would use that Mercator projection, it would look like this. which are used on the LMS. But here it's just a matter of the map projection.
So I would suggest keep some numbers or something like this projection, not to be confused.
Yes, I mean maybe at the others. Yeah, this is from Sumatra coming from east,
Okay.
kind of, and this is from South Atlantic because it's really far, so it's bended properly. Yes. Yes. So yeah, it's only a matter of projection. I tested it, so don't worry.
Right, thank you.
Nice to see surface waves again in Prague. And I have a very special question. If you try to go to high frequency surface waves from local earthquakes, I mean some earthquake here in Vienna, Wavefront or something like this, are there also stripes?
Not specifically, but the plan is that we will look at ambient noise, which means not only completely change the technique because we will use the cross correlations, but the main point is that we want to look at high frequencies. Moreover, we will not depend on earthquakes, so we can basically, because we will use one station as a virtual source and then calculate the cross correlations with a huge array. So the idea is that we can place our source anywhere we want to. We just need a station there. And we plan to look at, I would say, between 5, maybe 20, 30 seconds. So really on crustal surface waves to see if we can see these anomalies there as well. I would say the shortest waves I got was from earthquake from Greece because it's closer. So you can go for shorter waves. And I saw very nice stripes there. I'm not sure if I have the figure here, but I can show you later. It's actually in the appendix of one of the papers that Greek earthquake is shown here. And I didn't speculate what's the anomaly or what's the cause, but these are very clear stripes from the earthquake in Greece. I think at 15, 20 seconds, you see it very clearly.
Showed for the flickering of the stripes at 50, 60 seconds, that there was probably another source that, let's say, contaminated or influenced the wavefield. So I guess in the end, what you would want to do is to simultaneously invert for the position of more than one source that modifies the wavefield. Do you think that can work without non-uniqueness? Or rather, what is the minimum area size for the wavelength that we can do this without non-uniqueness?
The main problem with what we face here is that if you only look at one earthquake, you see the stripes. And obviously there is a huge non-uniqueness in lateral positions because it creates the stripes. So you cannot say in which, let's say, order of the stripe you are. So you need always at least 2 earthquakes, which are a little bit distant to illuminate the scatter from 2 sides. And this would apply for more anomalies the same.
But in order to know where you are in the pattern, you probably also need a minimum number of stripes.
Exactly. This is also why I included the very last slide about the AlpArray project, which should be even way broader than was the AlpArray. And our main, I mean, it's not like the reason why we do AlpArray, but one of the possible outcomes could be that if we really have such a broad array, we would see more stripes. And actually my hope is that one day I would see really the middle, really not just one part left, right, but I would see really the V shape so that I can say, okay, one earthquake is enough, because if I see both sides, I would use just one earthquake to locate the scatter. So yes, and the question is if we need to invert simultaneously. The problem is that I probably can model more anomalies with full waveform. But to set up an inversion for this full waveform would be computationally super expensive. The thing is that this doesn't take much time. On my old laptop, the inversion for the Camel volcanic line is done in 1 hour, because basically the calculation of the delay times is super fast. I don't calculate any full waveform. I just calculate the delay times for each point. So it's very fast. So I could easily did the grid search, which had 2 million cases, and within an hour you get the results. For the full waveform, it would be way more complicated. And the question is if maybe even with the simplistic inversion, I can invert one by one the anomalies. I can say, okay, I explain this one, then I can subtract it. And is there anything left? Can I explain it with the other anomaly? maybe yes, I need to try.
I was just wondering if you can have a setup where there's two combinations of source positions that create an identical deviation as well. Somehow through interference.
Yes, it can happen. And I think, by the way, also for one source, yes, you can have two anomalies having the same stripes. It's the case when you look at the earthquakes from Alaska and you look at the Iceland plume and the unmined plume. Actually, if you model, then they create really, they are shifted just by one stripe, but the positive and negative are almost the same. So looking at these Alaskan earthquakes, first, you cannot guess if it's Jan Mayen or Iceland. You need more earthquakes. So yeah, it's the same. More earthquakes for one plume or anomaly, or the opposite, yes. But you always need more races.